a star caused by the gravitational tug of an orbiting planet. Most of the discovered exoplanets have been gas giants or icy bodies. But a growing number fall within the so-called habitable zone, the orbital distance where conditions may allow liquid water to exist. Because liquid water is considered one of the fundamental requirements for life as we know it, such planets are regarded as promising candidates for further study. Among the most striking discoveries is WASP 96b, a gas giant unlike any in our solar system. Astronomers using JWST were able to analyze its atmosphere in unprecedented detail, detecting the presence of water molecules along with unexpected clouds and hazes. Before this, many scientists believed that such a planet would have a relatively clear atmosphere. Yet, the reality proved more complex. While WASP 96b itself is inhospitable to life as we understand it, the discovery demonstrated just how diverse planetary atmospheres can be. It also raised the possibility that many other exoplanets may host similarly surprising conditions, some of which could align more closely with what biology requires. Even without direct evidence of alien organisms, each new detection of water or of a planet residing in the habitable zone increases the likelihood that we are not alone. As humanity reflects on these discoveries, curiosity inevitably extends into more speculative territory. One of the most daring concepts to emerge in modern physics is the idea of the multiverse. The possibility that our universe is but one of countless others. Within this framework, each universe could possess different laws of physics, unique forms of matter, or even alternate versions of reality. Some theories, particularly the many worlds interpretation of quantum mechanics, suggest that every quantum event splits into separate universes with each outcome realized in a different branch of reality. The multiverse, however, remains speculative. Critics argue that without the possibility of direct testing, the idea may lie outside the realm of science. Supporters contend that it elegantly addresses puzzles such as why our universe seems finely tuned for life. Regardless of its scientific status, the concept captures the imagination, encouraging us to contemplate realities beyond our own. Just as earlier generations struggled to grasp concepts like dark matter, dark energy, and quantum uncertainty. Another mystery that unsettles astronomers is the phenomenon known as dark flow. First reported in 2008, dark flow describes the unusual motion of certain galaxy clusters that appear to be moving together in a specific direction at speeds greater than current models would predict. Ordinarily, the motion of galaxy clusters can be explained by the distribution of visible and dark matter within the observable universe. But in this case, the unusual drift suggested the pull of something beyond our cosmic horizon. Perhaps an immense structure or concentration of matter hidden from view. Some researchers propose that this gravitational influence could originate from realms permanently outside our observational reach. Yet, the concept remains controversial. Some studies support the data, while others suggest the effect might be an artifact of measurement or statistical chance. If dark flow is real, however, the implications would be profound, hinting that the observable universe is only one small region within a far larger, perhaps unimaginable cosmic architecture. Taken together, the observable universe, the hunt for exoplanets, the tantalizing possibility of extraterrestrial life, the speculative idea of the multiverse, and the enigma of dark flow all underscore the incompleteness of our knowledge. Every discovery expands what we know, but multiplies the number of questions that follow. Science, at its heart, is not a quest for final answers, but an ongoing journey toward deeper understanding. Each new advance, whether technological or theoretical, brings humanity closer to glimpsing the universe's secrets, while simultaneously reminding us of how much more remains hidden. The observable universe offers an extraordinary window into the past, revealing how matter, stars, galaxies, and perhaps even life itself emerged and evolved over billions of years. Tools like the James Webb Space Telescope serve not only as instruments of discovery, but as bridges through time, allowing us to witness the universe's earliest moments and to carry forward faint echoes of creation itself. Yet the significance of these discoveries extends beyond science into realms of philosophy, culture, and spirituality. If life were to be discovered elsewhere, how would humanity's sense of identity change? Would religions adapt, cultures shift, or civilizations redefine their place in the cosmos? Even if direct contact with alien life never occurs, the mere possibility of its existence reshapes our perspective. It emphasizes Earth's fragility and uniqueness as a cradle of life, urging us to value and protect our world more carefully. Scientific discovery then is inseparable from human responsibility. The more we learn of the universe's vastness, the clearer it becomes that our planet is both rare and vulnerable. In this sense, the pursuit of cosmic truth is as much about understanding ourselves as it is about exploring distant galaxies. Each revelation challenges our assumptions, provokes new questions, and stretches the boundaries of human imagination. The exploration of the observable universe becomes a mirror of humanity's own journey. A quest not only to chart the stars, but to find meaning within the infinite expanse of space and time. The further we push into the unknown, the more we discover that reality is not a simple structure, but a vast, layered, intricate tapestry beyond anything we can yet fully imagine. Every photon, every new planet, every unexpected anomaly is a reminder that the cosmos still holds mysteries we are only beginning to approach. To search the skies is therefore to search within ourselves, linking the quest for knowledge with the quest for meaning. The observable universe represents the portion of the cosmos that humanity can currently study, measure, and explore through the remarkable power of telescopes and advanced scientific instruments. Within this immense expanse lies everything from the planets orbiting nearby stars to the most remote galaxies that shimmer faintly at the edges of visibility. To us, this seems boundless, almost infinite in scale. Yet the observable universe does indeed have a boundary. This boundary is not determined simply by the limits of our technology, but is instead defined by the very nature of light itself. Light, which has always been our primary messenger across the cosmic abyss, travels at a finite speed. Because of this restriction, the universe we can observe is limited to those regions from which light has had sufficient time to reach us since the birth of the cosmos nearly 13.8 billion years ago. Each time we raise our eyes toward the night sky or point an instrument toward the heavens, what we truly capture is not the present-day state of stars and galaxies, but their ancient history. The farther away a celestial object lies, the older the light that arrives at our detectors. This transforms astronomy into an act of time travel, allowing us to gaze back into earlier chapters of cosmic history. Some of the photons striking telescopes tonight began their journey billions of years before Earth itself even coalesced from gas and dust, carrying with them stories written in light from an unimaginably distant past. This reality brings with it a fascinating paradox. The universe is estimated to be 13.8 billion years old, yet the diameter of the observable universe is approximately 93 billion light-years across. At first glance, this seems contradictory. How could a universe with an age of only 13.8 billion years stretch to distances several times greater than that in light-years? The answer lies in the dynamic nature of cosmic expansion. Since the explosive birth of the cosmos in the Big Bang, space itself has been stretching, carrying galaxies away from each other, as though painted on the surface of an inflating balloon. As light from the most distant galaxies traveled toward us for billions of years, the very space through which that light journeyed continued to expand. By the time those ancient photons arrived, their points of origin had been swept far beyond the distance that light alone would suggest. This expansion explains why we can observe light from galaxies that are now located more than 13.8 billion light-years away. The observable universe then is not merely a static sphere of reach, but a living snapshot of both distance and the stretching fabric of spacetime itself. Despite centuries of progress, humanity has only just begun to scratch the surface of this cosmic immensity. The universe is so vast and layered with mysteries that our understanding can only advance gradually through patient observation and daring theoretical exploration. Among the greatest modern tools for this exploration stands the James Webb Space Telescope, or JWST, a monumental achievement developed through international collaboration between NASA, the European Space Agency, and the Canadian Space Agency. This instrument represents the culmination of decades of innovation, extending the legacy of the Hubble Space Telescope, which for more than 3 decades revealed to us extraordinary sights across the visible and ultraviolet spectrum. Unlike Hubble, JWST specializes in infrared light, an ability of enormous importance because the expansion of the universe stretches light from distant galaxies into longer, redder wavelengths. Without such infrared vision, much of this ancient light would remain hidden from us. With it, JWST has become a kind of time machine capable of peering farther back into the universe's earliest epochs than any telescope before it. Already, its discoveries have exceeded expectations. NASA has announced that JWST has observed galaxies so distant that the light now reaching us began its journey nearly 13.8 billion years ago, only a brief span after the Big Bang itself. By capturing this primordial glow, the telescope offers a window into an age when the first galaxies were forming and the earliest stars were igniting. The images returned are not faint smudges of barely perceptible light, but dynamic, structured systems where stars were born at astonishing rates. These youthful galaxies appear to have evolved much faster than astronomers had previously believed possible, forcing a reconsideration of earlier models of cosmic evolution. Each observation suggests that the early universe was not merely a quiet, gradual unfolding of order, but a vibrant, turbulent crucible of creation, with galaxies and stars developing in ways that challenge our assumptions. Such revelations do more than illuminate the past. They also raise profound questions about the future of discovery and inevitably about the potential for life elsewhere in the universe. For as long as humans have looked skyward, the question of whether we are alone has lingered. The scale of the observable universe, with its hundreds of billions of galaxies each containing billions of stars, suggests that the emergence of life elsewhere is not only possible but perhaps even likely. And if the observable cosmos already teems with such abundance, it is natural to wonder about what